And the last data structure of this chapter is binary search tree. Sometimes we want to search an arbitrary element efficiently. So if we have a lots of elements in an array, then if it is not sorted, then there's no other way. Okay, so we have to check all the elements one by one, right? But if it is sorted, then we could take advantage of this property. Okay, so isn't there any tree-based representation method for that situation? Yes, there is. We can use a binary search tree. Okay, so in this section we'll talk about this binary search tree. So binary search tree is good for searching. Okay, so we'll talk about insertion and deletion, and also we will talk about search. Let's refresh our memory about binary search. So given a sorted list A, then we want to find a number x, target number x. Okay, since this one is sorted, then we don't have to look at all the elements one by one. Instead, we can actually look at the middle element first. And depending on the value of this middle element, if the middle one is smaller than our target number, then we can ignore the left half, and then we can focus on the right half. Okay, so on this right half, we do the same thing. We check the middle one of this right half, and then depending on the value of this middle one, and we can focus on the left or right again. So repeatedly we can do this, okay, or recursively. So by doing this, we can minimize the number of comparisons. So actually, if it is the best case, then we can find with the constant computation cost. If the middle element is the target number, then just one comparison is enough. But worst case, log n is enough, right? Because every time we can ignore the half of them. Okay, so log n is enough to find the target number if there is. And this list can be mapped into a tree. Okay, so now I want to introduce binary search tree. Okay, so before talking about binary search trees, then let me make a connection between this sorted list and this tree, binary tree. Okay, so in the list, the middle element corresponds to the root node. Okay, and then the left half will be corresponding to the left subtree, and the right half will correspond to the right subtree. Okay, then with this tree structure, we can compare the root node. Okay, and then depending on the value, and we can go to the left subtree or right subtree. And on the left subtree, let's say the root node is larger than our target number, and then we go to the left subtree. And in the left subtree, we do the same thing recursively. We check the root node of this left subtree, and depending on the value, then we can go to the left or right subtree. And we can keep doing this until we find our target. Or, if we meet the leaf node, and if the leaf node is not our target number, then we don't have that target number in this tree. Okay, so we will do this with the binary search tree. Okay, binary search is kind of data structure for this kind of purpose. Binary search tree is a tree which may be empty or satisfy these four items. Okay, first one says every element has a unique key. Okay, so far we didn't talk much about the keys. Okay, sometimes we might have a repeated keys, like 5 can have here and there, but in the binary search tree, the keys should be unique. Okay, next, keys in the left subtree must be smaller than that of root. Okay, this is important. The second and the third. Keys in the right subtree must be larger than that of root. Okay, it means it is kind of sorted. In the keys in the left subtree should be smaller than the root of the key of the root node. And likewise, recursively, left and right subtrees are also binary search tree. It means in the left subtree, the left subtree of the left subtree, the keys of the left subtree of the left subtree should be smaller than the key of the root node of the left subtree. You know what I'm saying? So basically, if you look at this figure, then and if you apply this binary search tree recursively, then you can understand what I'm saying here. Okay, and there is another really important property here. I mean, this binary search tree may not be a complete tree. Okay, in the max heap should be a complete tree, and it should be a max tree too. But in the binary search tree, it may not be a complete tree. So array might be really inefficient. Okay. So here are a couple of binary trees, and the question is, which one is binary search tree and which one is not binary search tree? Okay, the first one. It's not complete. It's not a complete binary tree, right? Not complete, and this is not the max tree. Okay, but then is it binary search tree? No, it's not a binary search tree because 22 is smaller than 25, but 22 is on the right side of 25. Okay, and 10 is smaller than 15, but 10 is right side. So this one is not binary search tree. This is binary tree, but this is not the complete tree. This is not the max tree. This is not the binary search tree. How about the second one? Okay, 30 is smaller than 40 and larger than 5, and 5 is less than 2. And now this is a binary search tree. And this is accidentally, this one is also a complete binary tree, right? And the binary search tree. How about the third one? 60 is smaller than 70, and 70 is larger than 65 and smaller than 80. So this one is a binary search tree, okay? And this one is not a complete binary tree, okay? And then this one is not the max tree, but this one is a binary search tree. Okay, here is a data structure for a node for binary search tree. And since this one is a binary tree, then we need two pointers, left child and right child. And we need a key, and also we need a data fields too. So we can have a structure for the data field, okay? Searching a binary search tree is quite simple. So if you understand the binary search, then it's kind of straightforward. Okay, if a current node is larger than target, then go to the left subtree. And if the current node is smaller than the target, then go to the right subtree. Okay, that's it. So let's take a look at this implementation. Okay, so in the search function, we get the two parameters. Okay, so tree node pointer and the target key. Okay, and if tree is null, then we return null. Okay, tree is empty, so we cannot find anything. So there is nothing there. And if otherwise, if key is the tree key, then we found it. So tree is pointing the root node of this subtree, and then we return the tree, which means this root node of this subtree is the target. Okay. Otherwise, if the key is smaller than the tree key, then we return search to the left child key. It means recursively we search. Okay, so if key is smaller than tree key, then we will look at the left subtree. Okay, So by calling a search function with left child pointer and the same key. Otherwise, we call the search function with the right child pointer with the key too. Okay, so this is it. That's simple. And as we did with binary tree for copying or some other functions, we can have another search function. In this case, we pass just the key. So these two search functions are different. Okay, so we use function overloading. So if we pass just one key, then we actually start searching from the root node. Okay, so this search root key will actually call the blue one. Okay, and also we can implement a search function iteratively. And as we said about the recursions, if we have a recursive solution, then we can come up with the iterative solution. But sometimes it's really hard. But in this case, it's not that hard. Okay. So search iter function will get one a key as a parameter, and tree starts from the root node. Okay, and then as long as tree is not null, then we repeat this while loop. And if the key is tree key is the target key, then it will return tree. Okay. Otherwise, if the key is less than tree key, then actually we move to the left subtree. Okay. Otherwise, we move to the right subtree. That's it. And we go back to the top of this loop, and we check if the key is the same as tree key. Okay, so this is an iterative solution for searching. Okay, and then as I said, if h is the height of the BSD binary search tree, then the search or search iter is done in h, okay, in a bigger notations. So it's all about the height of the binary search tree.